Hello students, this is my 10th video and third video on light. Light is a fundamental form of energy and electromagnetic radiation that enable us to see by being directed by our eyes, traveling in straight lines and reflected off objects. It exists as tiny packets of energy called photons and has electromagnetizes of both waves and particles. The different wavelengths of light are perceived by humans as different colors, such as the spectrum seen in the rainbow, and this form of the visible light portion of the broader electromagnetic spectrum. New Cartesian sign convention for spherical mirrors. The Cartesian sign convention for spherical mirror places the mirror's pole at the origin of the coordinate system, with the principal axis as the x-axis. Distances measured to the right are positive and those to the left are negative, while heights measured above the axis are positive and those below are negative. The incident light is assumed to travel from the left to right, and all distances are measured from the pole. The pole of the mirror is considered the origin. The principal axis is taken as the x-axis. All distances, object distance, that is u, I am introducing a new symbol u, that is a object distance, and image distance is v, focal length is f, are measured from the pole. Direction of the light. Incident light is assured to travel from left to right. Distance measured to the right to the pole are positive, already I told you, and distance measured to the left to the pole are negative. The height measured vertically upward from the principal axis are positive. Height measured vertically downwards from the principal axis are negative. Now, applications of concave mirror. So, suppose you are going to apply the Cartesian plane in the concave mirror, has a negative focal length. All the concave mirror has a negative focal length because its focus lies to the left of the pole. For convex mirror has a positive focal length because its focus lies to the right of the pole. Mirror formula for the spherical mirror. The mirror formula is 1 over f equal to 1 over u plus 1 over v. I already told you about what is f, what is u and what is v. F is the focal length, u is a object distance and v is a image distance. This formula relates the focal length of the spherical mirror, the object distance and the image distance from the pole of the mirror. So, how to use the formula? This formula is used to measure distances from the pole. All distances you have to measure from the pole of the mirror. You have to apply the sign convention here, and to calculate the unknown terms you have to use this formula. You can calculate the unknown terms. The formula allows you to determine the location of the image if you know where the object is placed and the focal length of the mirror. Then magnification. So, magnification is m equal to negative v over u. So, magnification equal to height of the object, another formula, over height of the image over height of the object, hi over ho. So, magnification m equal to hi over ho equal to negative v over u. So, that is a magnification of the spherical mirror, how much it can magnify. Now, refraction. I already introduced what about the refraction. Refraction of light is the bending of light as it passes from one transparent medium to another. This bending is caused by the change in the speed of light as it enters a different medium. When light enters a denser medium, it bends towards the normal, and when it enters a rarer medium, it bends away from the normal. I am repeating again, when light enters a denser medium, it bends towards normal, and when it enters a rarer medium, it bends away from the normal. Key concepts include the refractive index, which measures how much light bends, and Snell's law, which relates the angle of incidence and the refraction to the speed of the light to the media. So, dear students, you can see the slides here. So, it is a normal. Normal is a perpendicular line. So, here the upper portion is a rarer medium and lower portion is a denser medium. So, this is a light. When light is traveling, entering from rarer to denser, so it should be the actual path, but it will bend towards normal. So, this way it will bend. So, this is a path of the light rays, and see here, if it will enter denser to rarer medium, it will bend away from the normal. And refraction of light through the rectangular glass slab. So, glass slab, everyone must know about the glass slab. So, refraction of light through the glass slab is a bending of light as it passes from one medium to another at two parallel surfaces. First, bending towards the normal when entering the glass. See here the red color one. So, you can see the marker. This is the incident ray, and this one is a normal. Normal is a perpendicular imaginary line. So, this will be the actual path of the light. This will be the actual path of the light. But what will happen here? It will enter from air to glass, rarer to denser. It will bend towards normal. See here, the light is bending towards normal. Then again, glass to air, rarer to denser to rarer, it will bend away from the normal. So, this way you can explain how refraction will takes place in the glass slab. This process results in the emergent ray. So, this ray is a emergent ray. Okay. So, this process results in the emergent ray being parallel to the incident ray. So, this is the, I already told you, this is the incident ray, and the emergent ray is parallel to the incident ray, and the how much it is shifted, that is lateral displacement. How the emergent ray is shifted with the incident ray. So, here you can explain, I will explain about in detail. The first refraction I already told you, and the second refraction, so and the lateral displacement, everyone I have explained about this. So, you must know about here the angle, this angle is here, angle of incidence, this is the incident ray. So, what is the angle of incidence ray? Angle of incidence. So, you can determine, you can state that the angle between the normal and the incident ray. So, this is the angle of refraction, the angle between the normal and the refracted ray. This ray is a refracted ray, and this is the emergent ray. So, angle of emergent. So, the angle between the normal and the emergent ray. And what is the lateral displacement? The displacement between the incident ray and the emergent ray. Okay. So, here air is here rarer medium and glass is here denser. The law of refraction is the incident ray, the refracted ray and the normal all lie in the same plane. This is the first law. And the second law is the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant. This is known as refractive index, and it is also known as Snell's law. So, what is refractive index? It is a measure of how much light slows down and bends when it enters a material from a vacuum or air. It is calculated by the dividing the speed of light in vacuum by the speed of light in the material. A higher refractive index means light travels slower in the material, causing it to be bent more. Now, spherical lenses. A spherical lens is an optical lens with at least one surface that is a portion of the sphere, giving it a uniform curve. This design causes light to be refracted as it passes through, and the lens can either concave or convex. There are two types of lenses, concave lenses and convex lenses. First, convex lens. It is thicker at the center and thinner at the edge. A biconcave lens bulges outward on both sides. It converges parallel light rays to a single point called principal focus. Concave, that is a diverging lens, thicker at the edges and thinner in the middle. A biconcave lens curves inward on both sides. It diverges parallel light rays, making them appear to come from a single. Refraction by spherical lenses. In a convex lens, a ray of light parallel to the principal axis, you can see my pointer, after refraction passes through focus. In a concave lens, the ray parallel to the principal axis, it appears to diverge from the focus on the same side of the lens. And in a convex lens, a ray of light passing through the focus, see the cursor, pointer, after refraction goes parallel to the principal axis. In a concave lens, a ray of light directed towards the focus after refraction goes parallel to the principal axis. And in a convex lens and a concave lens, both are same here, a ray which is passing through optical center goes without any deviation. See the pointer here. So, without any deviation it will pass through. Now, images formed by a convex lens. First, position of the object at infinity. So, here this is an object, it is placed at infinity. So, all the rays coming from the object after refraction, it will bend towards normal. So, after refraction it will pass through the focus. So, you can get the image at focus. So, the image will be highly diminished, real and inverted. Now, the second position of the object is placed beyond 2f. So, here the first ray is parallel to the principal axis. After refraction will pass through the focus. The second ray will pass through the optical center without any deviation here. So, the meeting point you can get the image. So, the image exactly formed between f and 2f. So, it is real image, inverted image and diminished image. Diminished means it is smaller than the object. And the third position is the object is placed at 2f. So, here the same rule, first ray parallel to the principal axis, after refraction will pass through the focus. The second, the ray will pass through the optical center without any deviation. This both rays will meet at a point, you can draw an image in that point. Here the image is formed exactly to F. So, the ray it is a real and inverted image of same size of the object, and next position of the object is between 2F and F. Here this is the object. Same rule, first the parallel ray, after refraction it will pass through the focus. Second, the light ray pass through the optical center without goes any deviation. So, the meeting point you can draw image. So, here the image is very large and real inverted, it is enlarged image. And next position of the object is placed at focus. Same rule, first ray parallel to the principal axis, after refraction will pass through F, and second ray will pass through the optical center without any deviation. Here, see here, the both rays, refracted rays are parallel. That means what? We will get highly enlarged real and inverted image will get. And next position is between F and O, focus and optical center. This is an object. Same rule, the ray parallel to the principal axis, after refraction will pass through F, and another ray will pass through O without any deviation. But here it is diverged, never will meet. So, it will appear to meet the same side of the object is placed here. See here. So, this image is erect, enlarged image, erect image, and it is virtual image. So, what is virtual image? The image is obtained in the, it is for the lens, it obtained same side of the object. And the image formed by a concave mirror. So, there are two positions, one is at infinity, this position at infinity. So, all the rays coming from the infinite, the object placed at infinity. So, they appear to meet at F, they appear to meet at F. Okay. So, you will get highly diminished virtual and erect image you will get. And second position between infinity and F, the object is placed at infinity and F. Here the first ray is parallel to the principal axis, it will diverge, but it appear to meet through F on the same side of the object. So, second ray will go through optical center without any deviation. The meeting point you can draw an image. So, that is diminished image, virtual image and erect image. So, sign convention for the lenses. So, this same as spherical mirrors. So, no need to explain again. So, the sign convention of the mirror and the lenses are same, and lens formula is different. Here this is lens formula, 1 over V minus 1 over U equal to 1 over F. Okay. So, slight difference in the mirror formula and the lens formula, and magnification is same, height of the object, height of the image over height of the object, magnification equal to Hi upon Ho, but here M equal to Hi over Ho and equal to not negative, positive U over U. And power of the lens. So, in lens you must heard about the power of the lens. So, power of the lens equal to 1 over F, F in meter. So, the SI unit of power is diopter. So, 1 diopter is the power of a lens whose focal length is 1 meter. So, how much the lens can diverge and how much a lens can converge. So, that is a power of the lens. The power of the convex lens is positive and the power of the concave is negative. Thank you students for watching this video, and don't forget to subscribe my channel. Thank you and have a nice day.